Hello and welcome to the fifth lecture in the series of high frequency amplifier. As we have been discussing the BJT at high frequency, and today we will pick the topic of common emitter current gain when we have applied the resistive load. In previous lecture we have discussed that how the gain is related with the frequency when we apply the short circuit current gain. Yeah, and see today's topic is common emitter current gain with the resistive load when we have not applied the short circuit analysis. Then what will be the effect on the gain? Outcome of today's lecture and the question related to the today's lecture. So this diagram is the same as we have discussed in the previous lecture as well. This is the RL, which is now will be present in our analysis since we are talking about the resistive load. Okay, so we are not going to short this particular resistance anymore. So again we are applying the Miller's theorem. We are applying the Miller's theorem from RB-C and CC. Whatever analysis which I have told in the previous lecture, that prevails here. So if you are coming directly to this lecture, just watch the previous lecture for the further details. Okay, so RB-C and CC are the terms which are the feedback elements that needs to be applied the Miller's theorem, and here we have applied the Miller's theorem, and this is the value which comes out here. And again we want to calculate the value of the K. K is nothing but output voltage upon the input voltage, and it comes out to be greater than 1. Why? Because in the common emitter analysis we always say that the voltage relationship is always greater than 1. So 1 minus 1 upon K can be written as 1. Yeah, so if you want to calculate the new load resistances, since this value, the RL, the RCE, this RB-C upon 1 minus 1 upon K, and this CC 1 minus 1 upon K, all these four elements are in parallel. Okay, so we have to calculate likewise. So this is the RCE, this is the RB-C. Why it is RB-C? Because we have assumed 1 minus 1 upon K as 1. So this particular denominator terms removes from there. Okay, XCC is representing me the value of the admittance value of CC 1 minus 1 upon K. Yeah, and RL is the RL, that is the load resistance, and we are assuming the load resistance as 1 kilo ohms. So RC is nothing but 80 kilo ohms. From where this value comes out? From the standard value that we have already discussed in the first lecture. You can go through the first lecture of this high frequency amplifier, and from there you can note down the values of the particular elements. Yeah, so RC is 80K, RB-C is 4 mega ohms, RL is nothing but 1 kilo ohm. Here we are taking the value of RL as 1 kilo ohm. Yeah, and what is XCC? XCC is nothing but 1 upon 2 pi FCC. So we are calculating the CC as XCC, we are calculating the reactance. So reactance is 1 upon 2 pi FCC. Why we are writing FCC? Because CC is the capacitance value. What is F? F is nothing but the 1 megahertz. Again we are taking the F as 1 megahertz. It is not given, we are taking the F as 1 megahertz. Yeah, and CC we already know from the standard value, that is the 3 picofarad. This is the transition capacitance actually. So the XCC, by putting this value 1 upon 2 pi, this is the value of the capacitance and this is the value of the frequency in terms of the hertz. So 1 megahertz can be written as 10 to the power 6 hertz, and 3 picofarad can be written as 3 into 10 to the power minus 12 farad. So this comes out to me 53.05 kilo ohms. So this 53.05 kilo ohms is the value of the XCC. So now we are knowing the value of the RCE, now we are knowing the value of the RB-C, now we are knowing the value of the XCC, and we have also assumed the value of the RL. So by putting all these equations, all these values into this particular equation, we can calculate the value of the RL dash as 0.96 kilo ohms, and ultimately it is nearly equal to 1 kilo ohm. Okay, so now this is the diagram. What is the difference between the previous and this diagram? Previous diagram means the diagram which we have discussed in the previous lecture, the lecture number 4. Here we have not omitted this value of the output resistance because we are considering this RL. So we are putting RL dash, and IO and IC is again the opposite relationship. IO is nothing but minus SC, IO is nothing but minus GM into VB dash E. I do not have to tell you, this is the only current source which is present in the circuit. So IO becomes minus GM into VB dash E. This is my equation number 1. Now what is VO? VO is nothing but, what is VO? VO is nothing but which is the output voltage which is present across the RL dash, and that is nothing but the VCE. So VCE is nothing but, from this diagram you can already you can easily calculate that this is the current source which is available and this is the resistance which is available. So if I want to calculate the output voltage, what is output voltage? Output voltage is VO, or output voltage can be written as VCE. Okay, like this. So VO is equal to VCE, and VO equals to VCE can be calculated as this particular current source into this particular resistance. So this is how we have calculated the value. We are also knowing that what is K? K is VCE upon VB dash E. So what is VCE? VCE we have calculated like this: VB dash E, VB dash E, VB dash E cancel out, and K becomes minus GM into RL dash. So ultimately, if I want to calculate the value of the K, I can just multiply the GM into RL and get the value. So we have calculated the value of the RL. This is the value of the RL dash. RL dash is nothing but 1 kilo ohms, and GM we know the standard value of the GM is nothing but 50 into 10 to the power minus 3. Yeah, so ultimately it comes out to be as 50. So the value of the K is nothing but 50. Now from the input circuit, as we have done in the previous case of the short circuit current gain as well, this RB dash E and this RB dash C upon 1 minus 1 upon K is in parallel. So this RB dash, and we have calculated K as 1. We have calculated K as 50. So this particular value is no meaning for me. If K is 50, 1 upon 50 is 2 less value, and 1 minus something value is nothing. That will nothing create the impact on this particular value of the resistance. So ultimately 1K and 4 mega ohms becomes in the parallel, and again we can easily calculate that it comes out to be as 1 kilo ohms. So ultimately the resistance which prevails here is also the RB dash E. Now again CC and CC1 minus K is in the parallel, and when the two capacitances are in parallel, we just have the addition between them. So this is the ultimate value which we are getting here. This is the RB dash E, which is the total resistance present, and this is the total capacitance present. So again we have converted this impedance value into the admittance so that we can easily add it. So GB dash E is nothing but the conductance, which is the opposite of the resistance RB dash E, and this is the frequency term which gives me the value of the overall capacitance here. So we can just add these two values to calculate the overall admittance. Yeah, again VB dash E is nothing but IB upon Y, because this is the admittance value, and from equation 1 we have already calculated I naught as minus GM into VB dash E, and we know this VB dash E value from here, so we are replacing the value from here to here. So this IO is nothing but minus GM into IB upon Y, and we have calculated the value of the Y. So if you carefully look at the steps which we have calculated in the previous lecture and this lecture, it is the same. We are not changing anything. We have just applied one load resistance, and because of that load resistance, if you observe the previous lecture and this lecture, this 1 minus K term is coming. Rest of the thing is same. Okay, here I am using the term I naught because I am using the resistive load, and across the resistive load I naught is flowing. In the previous circuit, since we have short circuited the load, we have been considering the value of the ISC. So this is the just a small change in the denotation. So IO upon IB, this IB can be transferred here. So IO upon IB is nothing but again the current gain, output current upon input current. Okay, this is the same value of the GM which we have considered in the previous case as well. This is the same GB dash E, this is the same J omega, this is the same CE plus CC, only this 1 minus K term is added here. And why it is added here? Because we have considered the resistive load. Yeah, so again we will go ahead, and then I will finally discuss what is the impact of this 1 minus K value on the overall analysis of this particular current gain. Okay, so let us go ahead. This AI comes out to be as minus GM upon GB dash E plus J omega C plus CC1 minus K. We can again calculate the terms in so that we can get the relationship between the gain and the frequency. So I am dividing the equation both in numerator and denominator by the value of the GB dash E. So this GB dash E can be divided here, and this GB dash E can be divided here. This GB dash E cancelled out, and we have replaced the omega is again 2 pi f, and cc1 minus k is again there, the same term which we have calculated in the previous lecture. So I am repeating again, go through the previous lecture in detail so that you can relate it in the more illustrative manner, in the more comfortable manner. Yeah, so gm upon gb dash e, again we can find out the relationship. What is rb dash e? Rb dash e is nothing but hfe upon gm, so we can calculate it gb dash e as gm upon hfe, and from this relation hfe is nothing but gm upon gb dash e, so we can replace this value here. So ultimately this minus hfe comes out for me, which we have done in the previous case as well. And here 1 plus jf upon fh, so this value, this j is there, this f is there, now this value, this particular value, 2 pi into c plus cc1 minus k upon gb dash e. So if I want to introduce this particular constant term, this will be nothing but fh equals to gb dash e upon 2 pi c, where c is nothing but this. Yeah, c is nothing but c plus cc1 minus k. So if you can analyze yourself that what is the impact of the increasing the capacitance value when we have applied the resistive load, what is the impact on the overall gain? The gain will be further reduced. Why the gain will be further reduced? Because we have increased the term of the cc. Now the overall capacitance, if you want to calculate the overall capacitance, c equals to c plus cc1 minus k. Now let me put it like this, c is some value, cc has some value, and you are multiplying it with 1 minus k, and k is having also some value. So k will be 1 minus k, k will be some 50. We have calculated the value of the k here. No? We have calculated the value of the k as 50. So 50 comes here. So 1 minus k, 1 minus 50 becomes minus 49, and minus 49 gets multiplied with the cc, and cc gets added with the ce. So the overall capacitance will going to be reduced. So if overall capacitance will going to be reduced, the overall frequency term is going to be reduced. So you can say that the gain will be increased. Sorry, the gain will be increased. I somehow made this statement that gain will be reduced. The gain will be increased because you are ultimately making the frequency term on the lower side. And we have discussed in the previous lecture that if we are calculating the gain and frequency relationship, if you are increasing the gain, you have to compromise with the bandwidth, that is the frequency, and if you are increasing the bandwidth or frequency, then you have to compromise with the gain. So here we can say that if I put the load resistance here, the frequency term will going to be on the lower side, and we can have the better gain value. fh is the same, that is again the 3 dB frequency, the cases will be same, but the only difference is here we will get the slight higher value of the ai. Okay, so fh is the frequency which is the actual practical frequency when we analyze the bandwidth of the amplifier, because we can not always short circuit our output. So if output is present, the output load is present, if load resistance exists, the 3 dB frequency becomes the fh. So that fb which we have considered in the previous lecture, that is replaced by fh here, but that the meaning is not going to be changed. Then we had considered fb as the 3 dB frequency, here we are also considering fh as the 3 dB frequency, but it is giving me the more practical scenario of calculating the bandwidth versus frequency. Yeah, so that's all for the today's lecture, and we have come to know that what change occurs when we apply the output resistance, that is the load resistance, in the current gain, and what is the relationship between the current gain and the frequency, and how the term, the 3 dB frequency term, has changed from fb to fh. So just to conclude this lecture, we can say that if we introduce a load resistance across the particular transistor, the transistor amplifier, because of the presence of the load resistance, the value of the total overall resistance or overall frequency term will going to be reduced, and that will ultimately increase my gain. Yeah, so you can be asked to derive the expression of the common emitter gain with the resistive load RL and comment on the relationship between gain and the frequency. That's all for today's lecture. Thanks for watching. In the next lecture we will concentrate on some conductance value, some capacitance value which we have not considered yet. We have not derived anything about CC and CE, or not the derivation, discussion on CE and CC. We have discussed RB-E, RB-C, RCE, yeah, but we have not discussed about CC and CE in terms of the analysis, in terms of the J collector analysis. So a small lecture on that topic, and then we will go to the numericals. Thanks for watching today's lecture.